for that. So what I wanted to talk to today is a little bit about how I think about data mining and how I think about artificial intelligence in the context of scientific exploration and context of the oil business. And we could actually go on and talk about this for a long time, but I'm not going to do that. I think I have 15 slides here that pretty much cover the basic ideas, and hopefully this will work. Let's see. Okay, there we go. I am the interim director of the MS Analytics program. It's a 2-year program. This is an advertisement. Okay. So, 1 minute. Okay. This is the MS Analytics program that's taught right next door over here at the May School of Business. So if you're ever here on a Tuesday night or a Thursday night, you can drop in and see what's going on. They have classes that run from 6 o'clock till 9 o'clock usually. And I teach there in the summer. You'll see me goofing around here on Tuesday night and Thursday night in the summer. Now that program is, by the way, it's not just taught here, but it's also online. So about half of the students are not in Houston. Half of the students are other places in the United States. So we have people that are signing up from New York to California, and they can sit and watch the class live online. They take the same exams, do the same work, and actually work with the students that are in the program via remote connections. Students take courses in business, computer science, and statistics. Now there are several people in this room that are former students. I'll be introducing them here in a minute. There are approximately 50 students each accepted each year, and they go to classes for about 2 years. And the former director of this program was Simon Sheeter. How many of you know Simon? Australian guy, entertaining, okay. Unfortunately, he's a good friend of mine. Unfortunately, early in August, he called me in his office and said, "I'm leaving." I said, "What?" He had 45 students. So when he left, guess what? I got 45 new students, plus some other courses that I had to teach and so forth and so on. So he owes me, and he knows that. So I'm the interim director of that program. If you happen to have any questions, I can hook you up with the right people on that. If you know anybody that's interested in analytics and would like to go through a professional program, a 2-year program, let them know. It's a good program. The students that are here tonight, the past students, Andrew Silver. Andrew is here, and everybody, I think people know Andrew. Andrew, you graduated with Brian, and also with Diego, and Alejandro and some other folks. This was probably one of the best classes ever to graduate, 2018 last year. Tonight we also have Barbara Thompson and Sean Wright. Where are you guys? You're still here. Okay, good. They're going to be giving a little bit of a talk about what they did in the program in a minute. And then we have for the 2020 class, Adrian. Are you here, Adrian? I was told, I don't know Adrian. Jeremy, are you here? Let's see, Palomo and Obed. Okay, good for you. You drove up from College Station, or you're in Houston? Okay, good. Well, there are 3 other folks that are supposed to be here, and they didn't, I don't know what happened. Good to see you. All right. General concepts. I'm titling this conversation, The Art of Data Science. The Art of Data Science. And in talking with some of you here before this presentation, it seems to me this is an appropriate subtopic. Most of you have a scientific background or an engineering background, and so a lot of what I could tell you about the algorithms and such would be familiar to you, but maybe you haven't thought about the art of applying things in the context of what you do. It's no more true than, it's certainly true in the art of data science. It's very important to understand that idea. And the primary goal of data science and analytics is to solve real-world problems using data. That's the primary goal, and so that would be real-world problems, meaning decisions and forecasting primarily. The science of analytics assumes, this is important, The science of analytics assumes that the data you have adhere to a certain set of assumptions. And if those assumptions are correct, then the application of this science to those data to solve problems will be accurate. Now, the problem is that these are abstract assumptions. What does it mean for a set of data to be correlated or to be normally distributed? What does it mean for an observation to be an outlier? These are really statistically abstract concepts. And these assumptions that we make about data are almost never correct. Now, my first job with Chevron, I was pulling my hair out because I had been taught this is the way data is supposed to look and it's supposed to be like this, and if it's not there, God help you. Well, all of the data that I was looking at had problems. And it wasn't experimental data. A lot of this data were what I call happenstance data or historical data they pick up. They drill a well, they make observations on the well, but they didn't experiment on that well, did they? No, they're busy making money. They don't experiment with the well. So somebody said, what if we drill all the wells at 5,000 feet? Well, then all of the wells are going to be 5,000 feet and you won't know what's going on below there, or whether you drilled shorter, right? So if you're dealing with happenstance data, it's not experimental data. You don't randomly collect the data. You don't randomly make settings on the functioning of the apparatus or the log and things like that. So these create data problems. And how do you deal with that? This is the art of data science. How do we adapt the reality of our data to the theory and the mathematics and the statistics that we have in making our forecast? In this concept, here's another one. People say, okay, let's just collect more data. No! If you collect more data, you have more data and more problems. If you cannot handle your data you got right now, then maybe you shouldn't be collecting more data. Okay, I have so many people in the big data world, right? So I get dumped like millions of observations, thousands of variables. Yes, the computer can munch on that. I can handle that. There are algorithms that will deal with that. But is it really going to tell you what you need to know? Maybe not. Here's the situation for you. Bank asked us to develop an algorithm to detect fraudulent credit card transactions. Okay, 10 million observations in 1 month, right here. 2,000 observations on those data, right? You must be able to tell from that how we can automatically detect fraud. First question, of those 10 million observations, how many of them are fraudulent? Less than 1%. So the effective number of data points that they have is really small. It's not 10 million, it's a few thousand. Is that going to be enough to adequately develop an algorithm to detect fraud? The answer is usually not. This is called the rare event problem, right? You're trying to figure out how to detect something that's rarely occurring, and you think that I have a bunch of observations, but you don't really. The rare event problem is one of the headaches that you run into. Now you could see this in engineering as well. I have a student who was working on failures of natural gas compressors in pipelines. How many of you have seen one of those things? They're like a jet engine. Huge. Scary things. I mean, I don't want to be around them. Not me. No. I was talking about being a chemist. No. No acid, no fire, nothing like that. By the way, I was in the Army for 4 years, and yes, I had to blow things up, and that was a different deal, but I didn't like it. And I lost my hearing from that. So if you have a rare event problem, there are questions about whether the data that you have is going to allow you to figure out how to detect false credit. Or in the case of the compressors, we were looking for how do you detect the presence of a problem in the compressor that's going to cause a failure. And how often do you maintain that, inspect that compressor to see whether there is potential for a problem. That's a rare event problem, very difficult to manage. So this gets me to the art. What does the art of analytics means? It's involved selecting and applying the best available models for making decisions and forecasts. The best available, by the way, may not be good enough. So the art involves that question. Are we going to be able to solve this problem to the precision that we would like? And then how do we go about selecting those models and applying those models to do what we want to do if the data is got outliers and missing values and strange things? I was working for a bank once, and you're looking at the data and it goes like this. This was the accounting records, boop, like that. What caused the boop? Oh, yeah, we changed the way we recorded the data on that. Oh, really? Oh, good to know. How am I going to match up those data? Oh, well, I don't know. We can't, right? Right, we can't. So basically you couldn't use that data. Data pre-processing is very important in the art of analytics. Data pre-processing involves several things. First of all, identifying outliers. And secondly, estimating missing values. And there's some rules of thumbs for this that we try. How many missing values do you want to estimate? Well, not too many, but there are some default conditions where people will actually try to estimate up to 40% or so of the data. It depends upon what kind of model you want to use and what the data looks like. There are ways to do this. Not necessarily effective, but we have options for that. The other part of data pre-processing involves developing meaningful attributes from the existing data. So for instance, in the case of fraudulent credit cards, I have access to your entire bank account. I know what you bought, when you bought it, how much you bought, all that records in the bank. So how am I going to use that? Well, it turns out that the most important thing in that bank record is how often, when is the last time you went to a Chinese restaurant? When is the last time you bought jewelry? When is the last time you bought software? So there's a little variable that is called recency. When is the last time they used this credit card in Mexico? Never? Oh, boop, there goes the red flag right there, guaranteed. That's why most banks now, when you travel, they ask you, tell us when you're traveling, otherwise we'll cut off your credit card. That's basically what they're saying, so be sure you do that. This whole thing of data pre-processing is the art of data science. It takes up 80 to 90% of our work time, our efforts. So if somebody brings a problem to me and I'm looking at it, the first thing I'm thinking about is outliers, missing values. Is it a rare event problem? Do they know how the relationships among these variables in a meaningful way? Answer no to that? Oh, I can figure it's going to take a long time. Maybe too long. Next question is, when do you need this? In a week? Ain't happening. Okay? So data pre-processing, I'm usually thinking in terms of 1 to 2 months. And that's 1 to 2 months of honest, hard work, looking at data, doing graphs, of identifying issues that exist in the data, talking to people about why those things occur and that sort of thing. So the software folks would like you to think that all I got to do is take these numbers and put them in the software and boop, magic happens. And that's going to take about a day or two, right? Well, once the data pre-processing is done, that is true. Magic, boop, can happen. But the data pre-processing, which is more labor than software, can take a long time. Software can help you in this context, especially nowadays. Graphs and easily identify problems that are really how many missing values do I have and things like that. All right. SAS has something called SEMA, which is a good acronym or a good way of thinking about the process of data mining or analytics, is that we have to have, first of all, have a way to read the data or sample the data. Nowadays, SAS does very good with that. Python also. How many of you use Python? Anybody Python? Okay. Nice thing about Python is it'll read almost anything, just like SAS. And another thing that it'll do that SAS doesn't do very well, it'll get data off the internet. Python. So that's why we teach Python in our program, is that a lot of people nowadays want to grab information off of the internet. They want to read the news feeds, for example, and explore those news feeds to identify business opportunities or problems. Explore is that data pre-processing, looking for outliers and missing values. Modify is part of data pre-processing, creating new attributes that have more meaning than the original data. And then you have model. That's the part that the software folks and assess rather. That's the part that the software people love to talk about. This is neural networks, decision trees, regression analysis, and so forth and so on. That's where you'll find that. But the most difficult part and the challenge is really that first part of the outliers, missing values, things like that. So in Sas Enterprise Miner, this is deceivingly simple looking. This is what a program looks like in Sas Enterprise Miner. This is a program that's going to read data, look for outliers, fix missing data. These little boxes. These little boxes are actually like subroutines. You connect them together and you have a visual representation of the analysis that you're going to do. This is also part of what we teach in the program, is Sas Enterprise Miner. There are other solutions that work like this. There is a KNIME from Germany. Well, they're from, I want to say France. They have an office now in Austin, and they're based on R, I believe. And then there's another company that's based in Germany that uses different, something like Python. So in this particular case, what we're doing is we're reading the data. We are in that first square here, and then we're going to create new variables in the next box, transform variables. This sets up the metadata, that's information about what each one of these variables represents. Then we're going to partition the data into two pieces. A large piece that we're going to use to build a model, and then another piece that we're going to keep on the side for validating that model. Validation is a critical part of machine learning nowadays, is that if you build a model, usually you're either going to overfit or underfit the model, and so you want to be able to validate that model to see if you're overfitting the data. Okay? Now here's an example. How many of you know where Eagle Ford is? You probably do, right, geologists? Okay. If you don't know, you see that map on the left there? That's San Antonio in the middle, and then all those little triangles are wells. It's a large oil reserve in Texas. And I have a sample of that data. You can see it on your right-hand side there. That's the longitude and latitude of where these wells are located. I think it's 103 wells. And what we're going to look at is the EUR, ultimate recovery, oil recovery from those wells. And what I'm going to do then is, okay, okay, there it is, okay. So these are the variables that I'm looking at in the data. And I've cleaned up the data. These are already pre-processed, right? So there are no missing values, there are no outliers or anything like that. EUR is what we call the target. That's the thing that we're trying to forecast. And then we have QI, the initial flow rate, total propellant, total fracking fluid, the distance between the first and last preparation, that's C length, the stages, number of stages in the well. Total vertical distance from the heel, and then the difference between the heel and the toe, TVD, and then the latitude and longitude. Some people don't put latitude and longitude in there, but if you do put it in there, then it allows you to adjust for some of the geology that's changing over that oil field. And it turns out in this case that there is an issue with that. Oops, okay. All right. This is the usual approach. This is the approach that I learned when I was in college initially, regression analysis. I have a variable that I want to predict. I have variables I want to use to predict it. So I fit a regression model, and you can see here how it's doing. On the right-hand side, this is a graph of the predicted values versus the actual values. The R-squared in this case is 44%. From an engineering viewpoint, that's not very good. I don't know if you recognize that, but I like this R-squared to be well above 70%. 44% is pretty. You can see from the picture here, there's quite a bit of scatter. I'm not doing a very good job of predicting EUR based upon these variables. Now, another thing that regression analysis does, which is a good thing, is it gives us some ranking or priority. It says in this case that the variable with the smallest p-value, that's the right-hand column, is QI, the initial flow rate, right? And so it's good in that respect. It's saying that if you had one variable to use from this model, then you would use QI. And then the next variable, the next most important, would be, well, it's sort of a mix, but it's going to be the C length. No, VT, the total vertical distance to the heel. That has a p-value of 0.0048. So this is regression analysis. This is available in Excel. This is available in lots of software, right? So what are we going to do that's different? Lots of things. So nowadays, you have access to software. Some of it's like SAS is expensive. How many of you have SAS at your company? Okay. If you work at Chevron, you'd have SAS. Okay? And everything else. Because they used to tell me software is cheap, dry oil wells are expensive. So I said, how much? Really? In one conversation one day, yeah, about $25 million for a dry oil well, and most of them are dry. Oh, okay. That sort of puts things in perspective. So they don't mind buying a package that's going to cost $20,000, $30,000 for their employees. But nowadays you have alternatives like Python. Now here is an analysis that's being done, and the first thing I'm going to do on data like this is cluster analysis. How do these wells cluster? If I just look at the well log by themselves, which one appear to be similar and which ones appear to be different? In this case, I asked for 4 groupings, and you can see the clusters over there. The first cluster has 28 wells in it. The second one, 17. The third one, 24. And the largest cluster is number 4. And then what you see to the right of that is the average of each of those clusters for all of the other well characteristics. So from that, I can look at things like this chart that you see on the lower right-hand side is a graph of the average characteristic for a well for each of those 4 clusters. So if you can see, for example, that the red cluster here, you see that red part? That's cluster number 1. And cluster number 1, it has the highest values for total propant, total fracturing, sealing, and the number of stages. So those are the wells that have the large number of stages, the most propant, and so forth. If you look at the green curve, the one on the right here, they have high values for the other things, total vertical distance, latitude, and longitude. And so that would be cluster number 2. And then the other 2 are sort of in the mix here. So this is a cluster analysis telling me basically what's different about the wells, how they group up. The algorithm that's used to develop this is just simply looking at the commonality of these main characteristics in the wells, the well log, and then it uses that to decide, are you close to, in terms of these characteristics, to other wells. On the left-hand side is a plot for each of the clusters of the EUR. So which cluster has the highest EUR? Number 3. And I can tell then from number 3 up here, there are 24 wells there. And number 3 is the blue cluster, so that's the one that the high value is sort of in the middle. It's got high values everywhere, but low toe to heel distance and low total fracking, believe it or not, in these data. Now, if I took a different set of wells, I might get a different picture. I probably will, because there would be different wells. It's not, if I use the same wells and gathered more data on them, I should get the same picture. But if I grab another set of wells at a different location, maybe get different values. Now this is a decision tree. The next thing that I would do with these data, I love decision trees because they're easy to describe. You don't have to be a mathematical genius or a scientist or an engineer to figure this out. Decision trees are very easy to build. There are lots of software to do this. But what this says is that if I'm looking at EUR, I have 117 wells, and the average of those 117 is 102.6. If I was to look at one variable that separates the high from the low performing wells, that variable would be the QI. And what this tree is saying is that if the QI is less than 8,779, then there are 40 of those wells, by the way. The EUR is going to be about 69. If the QI is greater than that number, there are 77 of those, EUR is 120. So that's why I used yellow on the left and blue on the right. The yellow is the lower performing wells, and the blue is the higher performing wells. Then I can go over here and say, well, among the lower performing wells, what's the next most important thing? Well, it's QI again. Oops. Oops. Yeah, okay. Excuse me. Operator error. Okay, there we go. So in the lower performing wells, if we were going to separate them further, we would use QI and 5,000. And if it's less than 5,000, there are 10 of those. The EUR is only 41. Longitude becomes a factor. This is that spatial dimension. So if the longitude is less than 98, you get a fairly higher return EUR. And then if fracking fluid is less than 96,000, there are 8 wells there with 101 on the EUR. So pretty easy to read, right? You don't know the algorithm that's being used here. Trust me, it works. Okay. So the manager was asking, how do you explain this decision tree? You just had it. You just got the explanation. It doesn't take a rocket scientist to understand that. Oh, well, you could do this in a well, and everybody there would say, yes, I understand. Now, they may disagree with these results, but these results are based on the data. If they disagree with these results, then I would have to ask, what about the data? What's wrong with the data? Okay? Now, one problem with decision tree everybody knows about, if I make this tree bigger and bigger and bigger and bigger, it's going to fit the data exactly. I can make the R-squared 1 by making the tree really big. Now this tree is not very large. It has 1, 2, 3, 4 levels to it. It's not too bad. But if I keep dropping this out, I can get, see, R-squared is 64%. We went up from 44 to 64. I can make this R-squared even go higher by making the tree larger. That's the problem with decision trees. How big should I make it? How big should I make it? Okay? If somebody does an analysis for you and says, here's my decision tree, ask them what the R-squared is. Look at the lower boxes and see how many observations are in those lower boxes. Oh, there's 2 in there? That's too big of a tree, right? So what do you do about that? Well, here it is. Here's the solution to that. It's called a random forest. And so in a random forest, what we do is we build more than one tree. We build many trees, 100 trees. How do we do that? We resample the data. So I have 103 wells. I go in and pull 70 of the wells and build a tree. Then I go 70 other wells, build a tree. I do this 100 times. Not only do I sample the data, I sample the variables. I randomly select which variables I'm going to put in the tree. So then I get a better picture of what's going on. And then my forecasts are what are called ensemble forecasts. I average all the 100 trees to get my forecast. When I do that, look at the difference between the predicted and the actual, how much better it is. R squared here is 78%. You can see the predicted and actual look much better. Now, can I give you the coefficients for each one of these? No. But I can tell you which one is most important. Up there, it says on the top, here it says QI is the most important variable. You can see the little chart here by far. Of course, the regression cell told us that too. And the next one would be the total vertical length, TVD, heel to toes, C length, and so forth. So you can identify which variables are important, which ones are not, and you can get your forecasts from this type of analysis.